In this topology video, we're going to talk about paths and the path product. So let's start off with the definition about what a path in a topological space is. So let X be our topological space with topology T, and let's let A and B be 2 points that are in X. By the way, in this video, we won't really do a whole lot with the topology T, just kind of including it for the formality here. So a path from A to B is just a continuous function gamma, whose domain is the unit interval from 0 to 1, so all real numbers between 0 and 1, and whose codomain is our topological space X, such that gamma of 0 is the point A, and gamma of 1 is the point B. So in a picture here, gamma takes an input that's a real number between 0 and 1, and it outputs a point in our topological space. And the idea is that those points continuously vary from A to B. Also, gamma begins at A, and its terminal or ending point is B. And so to understand paths, you can start with whatever intuition you have left about parametric curves from Calculus 3. Sometimes those form a path. And as long as you just use the parameterization with domain from 0 to 1. And some intuition here, you can think about this domain from 0 to 1 as maybe it takes 1 unit of time to get from the point A to the point B in the topological space. So let's look at an example of a specific path, and let's let our topological space be R3 and consider this parametric function here whose x-coordinate is cosine of 2 pi times our input, whose y-coordinate is sine of 2 pi times our input, and whose z-coordinate is 2 pi times our input. And you might recall that this is just a helix that begins at the point 1, 0, 0, and then it would end at the point 1, 0, 2 pi. So a question you might have is, what do we use paths for? And I'll give you 2 answers to that. The first answer is you might be interested in integrating some function or a vector field along a path. For example, you're needing to compute the work done or flux, stuff like that. A second answer is a common objective in mathematics is to try to classify all objects with some property P. So for example, classifying all finite simple groups was a problem that took a little over 100 years, and it's considered finished as of 2008. So what we might be interested in is trying to classify topological spaces that have certain properties. And they have these properties, or we'll classify these topological spaces up to homeomorphism, meaning we're going to say 2 topological spaces are pretty much the same as long as there's a one-to-one correspondence between the things that we call open in each topological space. Another question you might have is, what kind of algebra can you do with paths that remembers or respects the starting and ending points of the paths that you're playing with? In college algebra, you learn that, well, you could take the sum, difference, product, or quotient of 2 functions. That's great algebra. Or you could take composition of functions and you get a function. That's all good algebra. What I'm going to tell you about is another operation we can do that you haven't seen before. We can concatenate 2 paths whenever one path starts where the other path ends. So in a picture here, here's my topological space. It's this torus-looking thing, and I've drawn 3 points, A, B, and C there. Let's say I've got a path gamma 1 that goes from A to B. Let's say I've got a path gamma 2 that goes from B to C. What I'm saying is I can concatenate them to get a path from A all the way to C. And so concatenating paths like this is sometimes going to be called the path product. So in some books they'll call it the path product is what I mean. That is what I'm going to refer to it as for the rest of this video. Now let me give you a more formal definition about what the path product is. So let X be our topological space with topology T, and let's let A, B, and C be points in our topological space. Let's say we've got a path gamma 1 from A to B. Let's say we've got another path gamma 2 from B to C. So notice that gamma 1 ends where gamma 2 begins. So it makes sense to concatenate them in your mind intuitively. So the path product, we're going to call it just gamma 1, gamma 2. We're not going to put a symbol between them. I like Gamelin and Green's notation. They don't put a symbol between the 2 things here, but maybe some books do put a symbol to indicate there's some kind of product. So the path product, gamma 1, gamma 2, it's going to be the path that starts at A and ends at C, and its definition is the following. So gamma 1, gamma 2 of t, where t is a real number between 0 and 1, it's going to be the following piecewise guy. It's going to be gamma 1 of 2 times t whenever t is between 0 and a half. And it's going to be gamma 2 of 2 times t minus 1 whenever t is between 1/2 and 1. And you might be a little bit worried, like, ooh, so like there's these two pieces here and they have this common input 1/2. If this is supposed to be continuous, remember the outputs have to agree there. And notice that this is continuous when t equals 1/2, because when I plug in 1/2 into gamma 1, I get gamma 1 of 1, and I know that that's b by definition of gamma 1. But when you plug in 1/2 into gamma 2, you also get gamma 2 of 0, which you know by definition that is b. Remember, gamma 2 starts at b. So I am at b at both these spots, so in other words, we're continuous when t equals 1/2. So some intuition here. What's going on with the formula? Maybe you can kind of see it. But the idea is, for this to be a path, right, you want to make sure that you get from the starting point to the ending point, say, in 1 unit of time. And so why don't we just run along gamma 1 and gamma 2 each at twice the speed, or at double speed is another way to say that. Let's illustrate the path product with an example. Our topological space is just the plane. Gamma 1 is this circle of radius 2, and gamma 2 is this larger circle of radius 3. The origin is going to be the points A, B, and C. Notice the path product traverses both curves in the same amount of time that it takes to traverse either gamma 1 or gamma 2 individually. So a question we might have is, what are we going to use this path product for? And the answer to that is it's going to be useful for classifying topological spaces, but we'll need a few more tools and ideas and some future videos in order to start on this task.